In complex, real-world systems, dense physical details often act as distracting noise when you try to optimize them. True optimization requires stripping away those physical layers to expose the underlying topology of the system. We process this abstraction using graph theory. We start by taking the individual, discrete objects within a system and representing them mathematically as vertices. We then draw edges. These are the mathematical representations of the exact relationships or boundaries connecting those objects. Once a system is reduced to vertices and edges, we generally face three distinct types of structural constraints: conflict resolution, edge traversal, and node traversal. Each of these real-world constraints maps to a highly specific algorithmic solution. By translating reality into graph theory, we reveal the hidden mathematical skeletons that dictate exactly what a system can and cannot do. Consider the constraint of conflict resolution. A university math department needs to schedule 10 classes for the upcoming semester, but certain classes cannot overlap because they share the same professor or require the same senior students. We map this conflict matrix by plotting the 10 individual classes as vertices. Next, we draw our edges strictly between any two classes that possess a time conflict. To resolve these scheduling overlaps, we use vertex coloring. The strict rule here is that adjacent vertices, meaning classes connected by a conflict edge, can never share the same color. This introduces the concept of a chromatic number. The chromatic number is the absolute minimum number of colors required to achieve a proper vertex coloring across the entire graph. In our scheduling model, that chromatic number translates directly to the minimum number of distinct time slots the university needs to run all 10 classes successfully. We rely on theoretical bounds to calculate this number, starting with planar graphs. A planar graph is one where the edges can be drawn so they never cross. The four-color theorem guarantees that any planar graph will always have a chromatic number of 4 or less. But physical systems often yield non-planar graphs, forcing us to use the two-colorable graph theorem. This theorem states that a graph is two-colorable if and only if it contains no circuits with an odd number of vertices. Look at this geometric graph with 6 vertices arranged in a hexagon and multiple internal connections. Searching the structure for odd vertex circuits, we see that every triangle formed by these connections represents a closed circuit of exactly 3 vertices. Because 3 is an odd number, the theorem dictates this graph cannot be two-colorable. We also observe the intersecting internal lines. The graph is not planar, meaning the four-color theorem is useless here. Without those bounding theorems, we are left with trial and error. Testing the nodes reveals that because every single vertex is adjacent to every other vertex, this specific graph strictly requires 6 distinct colors. Calculating the chromatic number bounds systemic conflicts perfectly. It ensures 0 resources overlap while dictating the absolute minimum capacity required to run the system. We encounter entirely different rules when our constraint shifts from conflict resolution to network traversal. Imagine planning a road trip through the American Southwest. Your routing constraint is strict. You must cross every shared state border exactly once. Translating the physical map into a graph, we assign the 9 states as our nodes and the shared borders as our edges. Navigating this network requires an Euler path. An Euler path is defined as a continuous walk through a graph that uses every single edge exactly once. Unlike coloring, finding an Euler path relies on a mathematical parity test. We calculate the vertex degree, the total number of edges connected to a single node. The rule states that an Euler circuit, which starts and ends on the same node, exists if and only if every vertex in the graph has an even degree. For an Euler path, the graph must contain at most 2 vertices with an odd degree. This square graph with a central vertex demonstrates how a path fails. The center vertex connects to 4 edges, an even degree, but all 4 corner vertices connect to 3 edges, giving them odd degrees. Because 4 nodes possess odd degrees, we surpass the strict limit of 2. No Euler path can exist here. Applying this logic back to the American Southwest, we can determine the viability of our road trip strictly by counting the borders of each state. Edge routing relies entirely on determinable structural laws of parity, completely eliminating the need for guesswork. But the mathematics change entirely when we adjust the routing constraint from visiting every edge to visiting every node exactly once. Consider the problem of seating 9 students around a round table, with the requirement that every student is seated only between existing friends. This node graph plots our 9 students, mapping their specific friendship connections as edges. This constraint requires a Hamilton path, or a Hamilton cycle, since they are sitting at a round table. A Hamilton path is a walk that visits every vertex exactly once, regardless of how many edges are left unused. Here we hit a profound algorithmic divergence. There is no simple degree parity test to prove a Hamilton path exists. We cannot solve the seating arrangement by counting connections. We are forced to rely on manual trial and error. Methodically tracing potential paths through this friendship network inevitably leads to dead ends, trapping unvisited nodes outside the sequence. Only through exhaustive testing do we find this single successful sequence, carefully threading the line through every node without crossing back over itself. Discovering this path proves the seating arrangement works, but verifying it requires brute force calculation. Vertex routing plunges systems into deep computational complexity, where elegant parity rules fail and discovery engines must take over. Graph theory proves that the specific nature of your physical constraint dictates the mathematical approach required to solve it. Resolving systemic conflicts requires calculating chromatic limits bounded by planar geometry. Optimizing edge traversal relies entirely on the strict calculable laws of Euler parity. And optimizing node traversal bypasses simple formulas entirely, entering the brute force realm of Hamilton paths. By stripping away the distracting realities of geography, schedules, and social dynamics, we isolate the pure vertices and edges underneath. By organizing data through pure abstraction, graph theory reveals the definitive mathematical limits of what is structurally possible.